Start recording. All right, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We are still in our sort situation, which, like I said, is a little bit of a dicey thing because we're doing a 2D game, but it's got some 3D elements in it, and whenever you kind of mix those two things, you kind of have to fall back to some touchy, sort of touchy-feely semantic rules for how things get sorted, and we've been sort of trying to work through how we think that will work out, and what's the minimum amount of markup we can do on our rendering to make sure that it will sort in some way that we feel is reasonable and plausible for the kinds of scenes and the kinds of entities that we know that we'll have. Now, we just finished getting our sorting working yesterday, but we haven't really debugged it, and we also don't really technically know whether our sort rule is going to work right, so we're kind of still in a little bit of an investigative phase. I got to jump right into it, though, so we'll have time to kind of pick around there. It's day 302, so if you would like to follow along at home, just open up day 301 source code. That's what we're looking at here. That's what I'm starting with on stream. So what I wanted to do, first of all, someone pointed out that I made a really bad typo at the end of last night's stream, which is to say that inside the render group, when I was sort of doing the code for creating the sort keys that we needed, instead of doing a plus equals, I did like an equals, and that's obviously not good at all. So you can kind of see here, where is that code get bound for? You can kind of see here where the code was a problem. It's supposed to be looking like this one where, we had the plus equals here. And so these are actually supposed to look like that. And in fact, I guess you could say you might do it like this. So it was supposed to be taking the y min and spreading it out by the height, and instead it was just setting it to that, which meant that all of our y bounds were just wrong. So that was obviously wrong, but I don't actually think that's the only problem we've got. I suspect we're going to have a bunch of problems here. And we also have, we have more stuff that we have to do as well. So we've got a lot of work to do. There's a bunch of stuff that we're going to have to do. So, for starters, I'd say that the first thing I would point out, if you take a look at what we're seeing on the screen, is just that there's a little bit of there's some twitchiness right to the sorting that you can see happening. And some of it's explicable, and some of it is indicative, I think, potentially of problems, but we'll see. And so I'm just kind of going through, I just want to kind of like articulate what I'm seeing on screen, so that you can kind of get a little bit of a feel for how I was thinking through this. So first of all, if you take a look at what's happening here with these sort of flashing, these bits that were kind of flashing, and as I mouse over it, of course, it decides to stop doing it. But there you go. So you see that's that flashing there? What I wanted to point out about that flashing there is that, well, that's a flashing that wouldn't necessarily concern me, because these are debug things anyway, and the reason that doesn't really concern me is because these are a bunch of rectangles which are overlapping and which have the same, essentially, z-plane and which overlap. And we never did a rule to try to differentiate those because we aren't really going to have that case, right? So that's not a case that worries me at all, and if we had wanted to make this work, we would have just increased the z of the border by just a slight bit to make sure that it sorted above it, and that would have been a fine solution in my opinion. I wouldn't have a problem with that. So the fact that that's twitchy doesn't worry me at all. What worries me quite a bit is this situation down here. So you can see that these guys, which are definitely below these sort of upper tier people, you can see that they're sorting above this tier. And what's more concerning than that is that they're sorting above it only some of the time, right? So what that says to me, or suggests to me anyway, and again, we haven't really looked into this in any particular detail, but what that suggests to me is that the rule that we defined, as I suspected, sort of mentioned as like, we're going to have to be a little worried about this, that suggests to me that my fears about it not being a straightforward sortable criteria are perhaps well-founded. Because what very well might be happening there is, depending on the order in which we hand these things off to the renderer, the sort may produce different results. And Again, that's just because of the way that our criteria happens to work. So, we have a sort of a question there that we can sort of think about, and it's really the question is, should we try to extend the sort rule so that it works all the time? Is there a way to extend it to be a little bit smarter so that the sort rule can produce complete ordering, so it doesn't have that if? Basically, and part of that is just, if you have an if statement inside a sort rule, then, chances are it's not going to be something that produces a correct, it's not going to produce a correct total ordering for these things. And the reason that I say that is because, well, it's unless you did specific work to ensure that the two halves of the if always produce consistent results, no matter which route you take through things, then depending on which items you end up comparing as part of the merge sort, you'll get different merges, right? So it's not unusual that that would happen, which is why I said I was a little bit afraid of it. It also is sort of in line with what Andrew Russell was talking about on River City Rampage Underground, or sorry, River City Ransom Underground, where he was talking about the fact that he had to use a more topological approach to actually do the sorting, which we might have to too, for all we know, right? We don't know the answer to that question yet. So the first thing I would say is that seems like a likely thing to me. I want to spend a few minutes on the blackboard looking into what we would do if we wanted to extend this out a little bit. Is there a way to make it more consistent without the if? And if there's not, then I'm going to go in and try to verify that that's what's actually happening. And actually, because it's easy to verify, maybe I'll just do that first, just to prove to myself at least that that's happening, because it's not that hard for me to sorry, I want to go in here actually. To know that that's happening. It requires a little bit of slowness here. Essentially what you can see is after we perform our sort, here's the sort happening here. We've got this check, if handmade slow is true, we'll go through and we check our sort of all of the things that we sorted to make sure that they're still in sorted order. And we do that by checking entry A against entry B for every pair of entries all the way down the list, right? But when I say every pair, what I mean is adjacent pairs, right? So we do 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5. And what that lets us know is that our partial ordering was correct, right? It means that we never compared two items and got the wrong, our sort never did something like insert two items that obviously failed their sort test next to each other. That never happened. So that's good. But what we don't know is if we were to check each entry against every other entry, would we ever find a pair that was missorted, right? And that's what we don't know. So what I'd like to do is sort of make two versions of this. One that is like, note, Casey, this is the partial ordering check. Only neighbors are verified. And the benefit to this is it's ON, right? We only have to loop through that list once. And so it's relatively speedy. We can just always turn it on. It's never going to be too slow to use. On the other hand, if I actually expand this out to check every pair, well, that's going to be ON squared. So we're not going to want to leave that on during regular usage, I wouldn't think. Unless we have a very low number of sprites, that's going to kind of come back to haunt us when we have higher numbers of sprites, because the number of checks is just going to be absurdly high. So this is something we only want to do during an active debugging scenario, in my opinion, so I want to make both cases so we can pick which one we use. So this is the ON squared, total ordering check. All pairs verified. So if we go ahead through here, and we could also do, I suppose we could save ourselves one repetitive loop, right? And do something kind of absurd like this. Yes, I'm getting a little crazy here, it's true. But what I could do here, right, is I could say like, oh, okay, give me a second loop here. And I guess in this case, technically, I'm not doing a second loop. But for the n squared case, what I'm going to do is say, well, I've got this index here, and then I'm going to have an index b, which is going to be this guy. And so then up here, when we do the partial check, I could just say, well, all right, index b can just be hard-coded to be this, and then we'll open a block that isn't a loop. And then we'll close the block here. Right? So that way, when we're in here, we do the partial ordering check by just grabbing, we'll just compare against this one. For index b, in the case where we want to do the n squared check, we can just say, like, we'll start at the index plus 1, right? And then we'll go all the way until we hit the very end of the array and just test all of them, right? So that would check every pair against every other pair and make sure that in front of returns the answer that we think that it should, right? Now, this is a little weird, though. I'm a little confused by this, and I'm wondering if this check is actually executing at the moment, because shouldn't this be giving us the opposite results? Take a look at this. If after we do the merge sort, when we go to check all these, we do index, from 0 to count -1, and let's say we're still in this case, like let's say we're still doing the ON partial ordering check. We come in here and we say, okay, from index equals 0 to index count -1, let's check entry A, which is, whichever one we're on, plus whichever one came after it, right, which is that index plus 1. And then I want you to tell me if the first entry is in front of the second entry. Okay, no, because we don't have a not there. So all right, so that's okay. Never mind, disaster narrowly averted. All right, so assuming that I didn't mess anything up there, if we run this now, we have this is sort of the old check. We know that nothing is failing in the old check. If I rerun it now with the new check, which I guess is not in the hot code reloaded, so we're gonna have to go. I'm hoping we get an assertion, and so there we go. We did get an assertion, and so we got an assertion on index 9 and index 40, right? And so let's take a look at what those two are. Entry A, entry B, and we can sort of see here what those two look like. Now, we can see that both of these have a ymin, ymax range. And so what that means is they are both sort of z sprites, right? They're both in the z plane. And we can see that the z-max of one of them is 0 and the z-max of the other one is 1.25. Now, what we know is that the 1.25 one in this scenario, right, should be drawing above should be drawing above the 0 one. So in this case, we should have entry B being above entry A. But that looks correct, right? Why are we getting that assertion? Because in this case, entry A is not above entry B. How did we get in here? Am I missing something? Let's step in there. So here we go. I backed the run, the instruction pointer back up so I could have the code execute a second time. So I'm going to go in here and say, are they both z sprites? That should return true, and it doesn't. So why doesn't it return true? Ah, okay, never mind. This guy isn't a z sprite. That was the problem. I was too hasty in that, I guess. Yeah. So never mind, that guy isn't a z-sprite. So that makes sense. So if that guy isn't a z-sprite, then we have to see right what the sort criteria would be here. He is not contained, and so since he's not contained, I think well, that should still sort by z, shouldn't it? Or I guess it sorts by y in that case. Yeah. So if it sorts by y, that's going to put me. B should have been behind A because its y was greater. And obviously it wasn't. So that's definitely a case where, yeah, that didn't come out the way that we would have expected it to. So not fabulous, right? Um, and I would like to see that update more. Is it really the case that that's the only error? I'm a little confused by that. Let's take a look here. I think what I'd like to do is change this from an assertion temporarily to something where I can just set a breakpoint. All right. So I just want to see how many different ones of these there are, right? So I just kind of wanted to know how many sort errors there were, if that makes sense. It looks like there's a lot of them, but they're all kind of very similar sort keys. Probably because they're rows of things in Y. Let's also do this. Here, let me take a look here. So let's also do a count. Sorry, my knee's been bothering me lately. Let's see. Make it a little more comfortable for myself. Probably not, but I can try. All right, so if I have, let's see, if I have all my sort errors here, and I can go in here and let me go ahead and sort of compile that in. And now I should be able to break at the end and just see how many sort errors I have. Let's see. Okay, so break here, sort errors should tell me. Of course, that's n squared, so I guess that doesn't really tell me that much about how many sort errors there were. All right, but point being, I think that at least verifies what I wanted to know in the first place, which is just how many of these particular guys were actually in, you know, how many, how likely was it that we needed a topological sort and weren't getting one? It seems very likely that that's the case. So the problem with that, just to sort of give a little bit more of a specific kind of, move this out of the way, just to give sort of a more specific description of what's going on here. And I don't actually remember, so it's day 301, right? Let's see here. 302. So day 302, sort partial ordering problem. So the problem that we're having here is just that when we compare, if we have three items, right? So we've got A, B, and C. Then the problem that we're having here is that we may compare these guys together, right? We may compare A and B and C, and we may never compare, say, A and C, right? Because the way a merge sort works is it doesn't compare every pair with every other pair, obviously, because that would be incredibly inefficient, right? And so what ends up happening is if we compare A and B and we say like, oh, okay, A should be in front of B, and then we compare B and C and say, oh, well, B should be in front of C, then we're going to think that the ordering is A, B, and C, right? But if we compare A and C, we may have found that C should have been in front of A. And so depending on which order these came in, if instead it had gone A, C, B when we fed it to the renderer, we then would have come up and said, oh, well, the correct ordering was actually C, A, B. Now, neither of these is technically a correct ordering because since we've written a sort rule which doesn't necessarily always produce transitive results properly, right, then there is no such thing as the one total ordering. And that's the thing that sort of Andrew Russell was getting at when he was talking about his River City Ransom stuff. It's just saying, hey, in this scenario, you're going to have to sort of decide, well, when you sort things, you have to look at which things are actually overlapping and only sort those and hope that you don't produce any complicated cycles in those. And if you do, you have to do something clever to break them, right? And so, that's certainly a route we could go by. We could first check to see whether two sprites overlap and sort those, and then draw them in sort of overlapping chains. That's certainly something we could do. But the other thing we can do is say, can we turn our partial ordering into a total ordering, right? And the way that we would do that is, again, we would have to come up with something that sort of does the 3D check a little bit more thoroughly. Remember, people were asking about this yesterday, like, why don't we just do a whole 3D check? And my answer to that has always been, well, we are, right? The question is just, how little of a 3D check can we get away with? Because the more 3D of a check we put in, the more 3D data we have to associate with all our stuff. So we're constantly making more work for ourselves as we go. So we want to verify at each step of the way that in order to that we actually need the data that we're requiring of the sort of the input phase, right? If that makes sense. So anyway, if we take a look at what happens here, right now we're talking about sorting objects where we either talk about a Z sprite, which is kind of like the top face of a cube, kind of a thing. Or we talk about a Y sprite, which is sort of the front-facing part of that cube, assuming that we're viewing things from here, right? Although one might argue that the Z is the more front-facing one since we're top-down. So I guess you might say the Z is front-facing for our purposes, and Y is kind of facing out the bottom of the screen, sort of, in a limited sense. So if that's the way we're looking at our sorting, then we have to ask the question, well, if we start sorting things by Y, let's say we were sorting two things by Y, and so we put one thing on this side and one thing on the other side. The problem that we rapidly would run into is this thing might be higher in Z than this thing is. But because we sorted them by Y because there was some interceding object that pushed one to this side and one to this side in the sort order, this is never going to sort above this in Z. So later when somebody else who's below this guy in Z sorts against this guy, it puts him in a place that's below this guy, which will always draw in the wrong order for this guy, right? So the question is there any way that we could get around that by saying, well, we need to sort these guys in some other way that's more consistent? And I think my assumption is there is no way to do a 3D sort that will actually produce that, but we might be able to. If we actually sorted these as as the actual planes, maybe we could do something there, and I'd have to think about exactly what that would be. If we want to compare two elements together, and one of them is a plane like this, and what we could do is we could potentially try to sort them by Z first, I guess, since we know what the upper bound of this guy actually is, and then only if we can't sort by Z could we sort by Y if they overlap or something. Maybe that would be a better sort rule, and I'm not sure. We can certainly try it easily enough. Stuff like that is not particularly difficult to try in our sort rule now that we sort of have it to play around with. We can leave this in here, and I'll just leave this as the assertion, because now we don't really need that sort errors thing. I was just kind of playing around with that anyway. We can certainly leave our slow verifier in there as well. The is in front of rule, this was our old one. And what we could do here is just sort of change the sort criteria selector, right? So what we could do is say, well, previously what we were doing to determine whether or not we were going to sort this thing by Z is we were looking to see whether the Y ranges of something overlapped, right? So if both things were Z sprites, we would sort them by Z. If the things were overlapping in Y, we would also sort them by Z, because then we would know they wouldn't be able to be sorted that way. But in the case where none of that was true, we wouldn't actually sort by the Z values. So what that means is the case where we weren't sorting by Z values would have been cases like, so let's say both things were Y sprites that overlapped. The problem that we were having there is just because we want to sort those things in Y, we then wouldn't, I guess once we sort those things in Y, they create sort of a problem space. Yeah, you know, I'll be honest, I don't really see a way of fixing that particular problem. I mean, obviously we could try to sort them by their closest point to the camera. You know, it's plausible that something like that could work, right? Where you'd have something where we would say, well, what's the closest point to the camera technically, given that we sort of know what the kind of movement is in Y for the transform that we're trying to apply. We could try to do that. I'm trying to think if that has any particularly problematic applications. Untangle. This cord is getting a little tangled here. So let's see. I guess what I was saying is, so if we imagine these as always being sprites that look sort of like this, and we're sort of sorting down here, we could sort of figure out what's your closest point to the camera, right? And the closest point to the camera is going to have a certain distance that maybe tells us the answer to that question. And I don't actually know how true that is. In the cases that we were looking at before, the intervals seem to not be particularly what we would want, but I suppose when we actually think about what these actually are in 3D space, it's possible that being close to the camera would be, how close they are to the camera would be enough to go on. Yeah, I don't really know. I don't necessarily think that that's true either. But it's hard to say. One of the things that's a little problematic is because we sort of did a relatively hacky, we don't do a standard orthographic transform, is that it's a little bit tricky to figure out how far away things actually are from the camera. And the reason for that is we haven't really defined what exactly happens when things kind of raise up on the Y plane, based on Z, right? Like right now, I don't even think we're really even doing that. But that's kind of the thing that would be important for us to know there, is sort of like how much closer to the camera you get when you go up or down on like a facing card and stuff like that. But if we were going to do that, well, let's just take a look. Because, like I say, I certainly don't know the correct answer to any of these particular problems. Like I said, I've never really done a 2D sort of thing like this before. So it's hard for me to really know in advance what's going to be a good answer versus what's going to be a bad answer, if that makes sense. So let's take a look here. So if we do the get render entity basis p, and we look at what's happening to our transform, then we can sort of see that once we actually put the Z value in here, we would know whatever that percentage would be what we would multiply the height by in order to get the closest point to the camera in Z. So I would say, and since Y itself doesn't actually change the sorting in that sense, like, think about this. Since we're sort of saying that things are sort of tilted at an angle here, right? We're sort of saying that, you know, here's the ground and we're looking down at it. We're never really actually constructing this space explicitly at the moment, right? And I wonder if that's sort of something that we've done incorrectly. Like, I wonder if we want to actually do the transform that this implies with the actual camera looking down on it with an actual orthographic transform. Because if we actually did that, then all of this would sort of be a little bit more academic, in the sense that, like, oh, okay, then it would be really trivial to just go, well, what's the closest point to the camera? Because the closest point to the camera is just a subtraction of whatever your maximal point in z is, you know, to here. And you don't have to really think about the y at all, because that's going to be automatic. As you get closer this way, you just will get closer to the camera in that sense, right? And I guess I shouldn't say that because it really looks like this, right? In an orthographic sense. So yeah, if you have an orthographic camera looking at the scene, like so, then effectively what we have is we have these kind of lines coming at it. And so that should mean that we would always get lower distances as things move closer to the camera, right? Using the orthographic, you know, distance to that plane. So effectively what we're doing is we're saying, what's the distance to this plane that is the camera plane? You know what I'm saying? And when we have things that are z height, so I guess we could just take the distance to the camera plane. That's actually relatively straightforward, right? Because if we want to know the distance of something to a plane, you know, all we need to do is measure its distance along the plane's normal, right? So we know what that normal would be because we're going to define how sloped down the projection is going to be. Once we define that normal, all we would have to do is take the dot product of whatever this normal is, right? We'd take the dot product of whatever that normal is with the three-dimensional point we're trying to measure, and that's how we would get, you know, the distance along it. Now, obviously, we need to know where this plane is, but we know the camera is at 0, so we kind of already know what that plane is. So we just take the straight dot product would give us how far along, how far we would go from the plane out to the point we're talking about. So if we were to do that, for each card, and we always just take the topmost point, you know, would that be sufficient? And I'm not sure I know the answer to that question. So let's think about it for 1 second. Suppose I have this dude here, right? And I want to take his topmost point. And maybe he looks like this. In this case, you can certainly see that that would not work. This is why we discarded these cases before. Because this long piece here is always going to appear to sort closer to the camera than this one. In fact, I think that's the way we can convince ourselves that the 3D sort doesn't work, right? Because it requires a point-by-point sort to know that this part of this guy is behind this one. So that's why we need the sort of weird rules about sprites sort of coming together in order to resolve those things. Because in order to resolve something like this, we would have to do a point-by-point comparison in order to know that this part should be drawn behind this part. Because otherwise you'd say, well, this is the closest point, right, to the camera, so this whole sprite would have to be drawn first, and that's not correct. This is actually the one that would be drawn first, right? So I think, again, that sort of suggests that either you need to do sort of a fully 3D position z-buffer thing, or you need to go with something that's going to handle the topological sort properly. So I think I've relatively convinced myself just by looking at that. It does seem to me that that means if we want to try and go this route, then we're going to need something that's going to take a look at sprites that overlap, and when it finds sprites that overlap, it's going to have to perform those sorts specifically. That at least seems like the case to me. And that's relatively tricky, right? Because now we have to actually think a little bit more about whether these sprites, kind of, whether their actual screen space bounds line them up or not. So yeah, how do I want to approach that? It seems like that's not something that wants to get sent down through the renderer. And so that seems to me like, again, that's going to require, now thinking about this as something that's built outside as sort of the sprite list that then is walked as a tree, and as a graph, and then we actually sort of try to sort that graph more intelligently, right? So yeah, let's try. And I guess, like I said, I'm not really sure what's going to happen here. But let's try to start building something like that. And I think we might have to try to do this sort of in passes because it's going to be relatively complicated. So I'll start doing it now, but this is probably going to be a thing for next week. Let's go ahead and take a look. So let's just make, I guess we can make this in here. But what would we actually need? And let's say I did this in the least, we won't try to accelerate it first. I'll do it in the dumbest possible way. So let's say we had a thing, a function here that's like, resolve sprite graph or something, And so we're just going to go full pull. Oops. So what do I need to do I guess I should really say, build sprite graph. At least first, because we have to actually make one of these things first. So in order to build a sprite graph, I would need a list of sprites. So I would need something here that would have information like, okay, here's the sprite. And I would need to have essentially the sort of sort key information I have here, but I would need also some more information about whether the things overlap in screen space, right? So if I think about this, I'm going to need the original sort of screen space positions of these guys. So we need min p, or screen min p and screen max p, something like this. So I can tell if these two things overlap. And then I would need the stuff that we actually would use, like I said, for the sort. Which would probably be that zmax at the very least. So I don't know if we would want the ymin, ymax, because we can probably use the screen ones for that, I'm guessing. But we'll find out in a second. So we would have something like this, where we've got, a sprite node or something like this. And each one of these things, we would have a list, and we'd have to then build a graph out of the list, right? We'd have to sort of have a idea of the edges in there that sort of connect these sprite nodes to each other and say, this sprite node's in front of this sprite node or something like that. So let's suppose I had a list of these things. Here's the input nodes. And maybe I have an input node count. Excuse me. So if I take this input node count, and I've got the input nodes, and here I go and I say, okay, let's go through, node index A equals something. Node index A is less than input node count. And node indexes go like this, like so. So if I was to compare every node with every other node, right? So I'm just doing the absolute stupidest thing possible here. I could then say, I'm going to do this in the exact same way I was doing it before, and also I guess this would be -1. So if I go through every possible combination of these guys, and I should also probably check, make sure we actually have some. I do not know what that just did. All right, there we go. So if I go through all of these indexes so that I can have both my nodes, what I could do here is say, let me compare these two nodes with each other to see whether they overlap in screen space. So I'm going to say input nodes plus node index A, input nodes plus node index B. So I grab out 2 of these sprite nodes, and then I want to know, like, if overlap, there's screen overlap for A and B, then I know that I have a case where I need to determine which one of these 2 would appear in front of which other one, right? So then I would have a notion of a sprite edge, and the sprite edge would just be, in this graph, a connectivity between 2 sprite nodes, right? So it would have like a, index A and an index B of the sprites, and it would say like, oh, okay, this index is in front of this other index or whatever. And so, maybe I could do this in front and behind. So basically I can add an edge and say that this sprite is in front of this sprite, or this sprite is behind this sprite. So it's a directed edge. For those of you who don't know any graph theory, I suppose I should mention this really briefly. So there is such a thing as graph theory. We don't really cover it on Handmade here. We haven't really had to do much with it. I don't know how much we'll do with it. There might be a little bit more of it when we do world gen. It's definitely something that you need to know if you're doing game programming in a broad sense. It comes up in various places. So it is relevant, and I wouldn't discourage anyone from reading more about it. But basically, there's, in graph theory, we essentially have the concept of, nodes and edges. And what we're talking about is building a graph where we've got some number of nodes, and these nodes, have something in them. And then we have some number of edges between them, right? And the edges might also have data associated with them. Maybe I've got some data associated with these edges as well for some reason. Who knows why? I have no idea why they would, but maybe they do. I don't know that many Greek symbols, but let's say there's some of those. So anyway, you get a situation where you construct some meaning out of this usually in the context of your program. And so for the case that I'm talking about, I was sort of saying that the nodes of this are going to be sprites, and the edges of this are going to be information that says that one sprite is in front of another sprite, right? And the reason we want to do this is, again, harkening back to the River City Ransom Underground case, we want to kind of say, well, we're going to define some semantic information where we say that this is supposed to be in front of this is supposed to be behind this, whatever. We want to define that and then have the game have a solver that will go in and figure out what the order is that you can draw these sprites in order to satisfy as much as possible as what the graph said to do, right? Okay. So graph theory is basically algorithms that study these sorts of things and how you can determine stuff about them. For example, in this case, you might say, oh, maybe I want to ask some simple questions about the graph, like what's the maximum number of edges that emanate from a node, or how many times could I get to this node by different paths, or stuff like this. And specifically the kind of graph that we're talking about here, we have what's called a directed graph. And the reason it's a directed graph is because of the way that I talked about my edges. We didn't say sprite A is connected to sprite B. If we did, that would be an undirected graph, because we're just saying that there's an edge between A and B, and we don't have any other thing we want to say about it. But in our case, we're trying to specify a directionality to that connection. So not just some data, but an actual meaning in the graph. And what that means is that our edges are directed. They have the notion that, say, like A is in front of B, so there's a natural order to it. C is in front of A or something, right? And we would then say, well, the base of the arrow is in front of the target of the arrow, maybe, or who knows what, right? And so once we assign that meaning, we then create a specific type of graph that's a directed graph, which is to say that its edges have direction to them. And furthermore, we would want to have one step up from that, which is a directed acyclic graph. Now, a directed acyclic graph is a graph that doesn't have any cycles in it. So for example, this right here is a cycle. If I start at C, I can go to A, I can go to D, I can go back to C, and I can just keep going around and around and around, right? Because the edges flow in that direction, right? On the other hand, if I was to create a slightly different graph, one that looked like, for example, this, now I no longer have an acyclic, now I no longer have a cyclic graph, I have an acyclic graph. Because no matter where you go, you always end up at B, right? There's no way to go, I can't cycle. No matter where I go, I always end up getting forced into B, right? I always end up getting forced out to a leaf. And so directed acyclic graphs, or DAGs as they're often called, are super nice because we know there's sort of that total ordering to them, right? And that's exactly what we want for our sort. So we want this because if we had this, we would know we could always draw everything, because we always know there's a chain for every set of sprites that we can follow to draw them in the correct order. We probably won't be so lucky. We'll probably end up having something like this where we can create a cycle. And so this is, again, getting back to what Andrew Russell was talking about in his blog post. If we got that cycle, we have to break it somehow. Because if A is supposed to be in front of B, and B is supposed to be in front of C, and C is supposed to be in front of A, there's no way to ever draw them in order. You've created a cycle. And so if we're saying that we're never going to split sprites, we don't want to solve it that way. So if we never want to split sprites, then what we have to do is acknowledge that fact that we have a cycle and just kill one of the edges arbitrarily, right? And we can sort of make that determination about which edge to kill in a number of ways, like which sprites have the least overlap might be a good way of doing it. Which sprites are closest to being together, I don't know. But there's a number of metrics we could employ to figure out which of the edges would be the best one to kill in a cycle. And we would just kill edges in a cycle until we got a directed graph that didn't have any, a directed acyclic graph so it didn't have any cycles. So that's the part of the graph theory that we're talking about here. So basically what we'd say is, well, okay, if these two things overlap on the screen, then what we're going to do is we're going to add an edge here, right? We would add an edge. So we'd add a sprite edge, and the sprite edge would say, if these two things overlap, we just want to know which one's in front of and which one's behind each other. Well, we already have that ability. So we can go up here and take our in front of code, and we can just call that, right? So we can just do this right here. So we can say, like, if is in front of bound A and bound B, like so. And if A, in this case, if A is in front of B, then we would add an AB edge, and in the other case, we'd add the BA edge. Right? In the case where they don't overlap, we just wouldn't add an edge at all because we don't care. If two sprites don't overlap in screen space, we don't care what order they draw in because they're never going to occlude each other. So that doesn't matter. All right, so in this case, we've got sort of the sprite bound A, sprite bound B situation. What I'd like to do here probably is, well, I don't know. I guess I'll leave it like this for the time being because we don't really care about it too much. I'll just construct these two directly. But eventually we're going to want to regularize the data format anyway so that we don't have to do that. So it's y min, y max, z max. So the z max is transferred directly. But the y's, I think we would do sort of like this. So there I've created the bounds, and then we can use ours in front of. We add the edges, and off we go. And so really all we would need to know is there a screen overlap? And what we could do here, we could even lean on, if we wanted to, our rectangle concept, right? So we could even say, we have to have a rectangle area here. And if we did that, then we would just actually say, like, if they intersect. So I'm going to take a look at our math here. So we have a 2i intersect, but we don't have a 2 regular intersect, which we would need, right? And I don't see there. So I'm going to go ahead and grab this guy and make one for our 2 case. Let's see, is inside. Oops. And so in this case, we're just not going to check the Z. But otherwise, it's exactly the same. So there's our rectangles. And so all I would say here is like, okay, if our rectangles intersect for A area, or A screen area, and B screen area, then I would know that these are 2 people that have to have edges constructed between them. So in the case of, I guess the other thing we could check is if their z's were equal, we wouldn't necessarily have to do anything if they, yeah, there's some things we could do there. But anyway, so point being, if we construct something like this, then and of course I have to change this to screen area. I don't remember what our convention was for rectangle 2s here. I'm going to take a look. Rectangle 2. Where is that defined? Is that in the platform code? It is. So it's min-max. So that would basically be what would construct the graph for us, and then we just need a way of recording those edges, right? So we just need, we would just have some temporary memory where we just put all those edges in there, and off we go. Now, unfortunately for us, this is actually going to be a little bit dicey, because as we're constructing this graph, we also have to figure out how we're going to sort of more quickly access it, right? So we're probably I'm going to leave this unimplemented, because until I know a little bit more about how we need to walk the graph, until I know more about how we're going to walk the graph, I don't feel like I'm going to be too comfortable with that, right? Because we're probably going to have to do something like, for each sprite node, have a list of the edges that come off it so that we can quickly get to them, rather than having to sort of check through that list the whole time. But at least this is the code that we know that we would be executing up to the point where we actually have to add the edge. So that is how the sprite graph would be built. And you can see that this is an n-squared problem, so what we would need to do shortly after doing this part of it is we'd have to do something that partitions the screen up into subrectangles for purposes of building this graph, probably so that we would not have to check every one against every other one, right? In terms of the screen area overlap. So that's also something that we'd have to do at the outset, because basically looping over every node for node index A is not acceptable. This would have to loop over only ones that we knew were roughly within a similar screen bound, if that makes sense. So yeah, that looks like how we would pretty much handle the sprite graph. And then we'd have to do sort of our testing on it. Now, the other thing that's sort of questionable here is, if you look at how much work that's going to go into this, the other thing that we kind of have to ask ourselves at this point is, like, would we rather figure out a way to break our stuff up into z-bufferable pieces, right? Because that's the other route we can go with it. We can just say, like, well, let's actually try to put these cards in actual 3D. And I don't really know. But you can see how much work's going to be involved here. We're going to have to do a spatial partition for this. We're going to have to do an is in front of. Then we're going to have to walk the graph. And we're going to have to figure out which cycles we want to remove. It is a lot of work. And it's kind of, I'm wondering whether that's going to just be, it's going to bog us down in terms of performance when we want to run on GPUs, which are already going to be capable of doing z-buffers fast enough. At that point, it's like, well, should we just use the z-buffer and be done with it? Because that will be faster than trying to run the sorts on the CPU, probably, if we push the sprite count up high enough. You know what I'm saying? And I don't really know. Right? You know, for transparent things, obviously we have the problem where we would have to sort anyway. And so part of it's just saying, well, you know, if you actually just bite the bullet and have your sorting be a primary thing in a sprite engine, it means that you can lean on that for transparency as well. And then you can do whatever kind of transparent effects you want because you know that they're always going to be sorted into the scene in the right order. But I don't know. So we'll see. That's probably it for today because I don't really want to actually start going into that into more detail because I feel like, you know, we're going to be out of time in like 2 minutes anyway. So I'm going to go to the Q&A, but that's basically what we're looking at, and I'll F0 this out so that it won't cause any code problems. But there we go. One thing we could also do, you know, in that case as well is for these sprites, we also have the option, certainly, of, you know, if we ever went to optimize our software renderer, the fact that we're bucketing sprites by part of the screen, that would also, we could leverage that in the software renderer to only consider sprites that overlap a tile for tiled rendering, right? So we could also get dual use out of that sort if we wanted to. Anyway, so I'm going to wind it down, and we'll readdress this in next week's streams. Rome 0010011. How much more work would you have to do to get a full 3D sorting? I feel like I'm not explaining this properly because this question has come up so many times and I feel like I'm not communicating it well. Full 3D sorting is really easy. The problem is we don't have 3D data. That's the problem, right? You can sort 3D points trivially. You just use the distance from the camera and you're done, right? But the problem is if you don't have 3D data, you can't sort 3D data. And so in our situation, you know, we have the problem of here's a sprite. It represents a fairly complex 3D object, but it's just a flat plane. There is no way to really, you know, sort it into a scene correctly because it's a card, and that card doesn't have the meaning that your eye thinks that it has, right? And so we have to decide how much 3D construction we're going to make for our actual objects, if that makes sense. And I don't know the answer to that question, right? I really don't. And you know, obviously we won't ever be able to get full 3D data because the things don't exist as 3D objects. They've only been painted as images. Nobody knows what they look like in 3D, right? Rome 0010011. I mean, use fake 3D data since our cards are essentially flat. We can give an epsilon width to it for the sorting. Yeah. So in order to do that. Like I said, I really just don't know how to explain this. Sorry. I'll try one more time, and you can tell me if this helps. Suppose I have two 3D objects. Here's one. Here's another. Right. Here's the camera looking at them, and I want to know which one I'm going to draw first. There is no way to sort these two 3D objects by which one the camera hits first, because there's no such thing as which one the camera hits first, right? That's not really a thing. Being humans, we happen to know that because of the shapes of these two objects, in the places where they happen to overlap, we could always draw this one first, and it would always be correct from this perspective, right? So that's good. That's the kind of rules we were trying to think of when we were talking about our sprites, which were like kind of fake cards there, okay? But if we actually wanted to sort these properly in 3D, using actual 3D data, so suppose we actually have these as 3D objects, then the answer is for every ray that comes out of the camera, we must see which object gets hit first for that ray, for that pixel, right? That's why you use z-buffering in 3D rendering, because let's say, for example, that what these things actually look like is something like this. And now I ask you, which one of these should be drawn first? Well, the answer is, which part? If I'm looking at this part of this object, then this one should be drawn first. If I'm looking at this part of this object, then this one should be drawn first, right? And that's because their shape is complicated in 3D. It's not straightforward. So once you start approximating things by cards, you're into a case that's more like this, which is to say, there probably is a rule that would allow you to draw one thing first and then the other thing, without having to do a per pixel comparison. And the reason for that is because you know that you don't have any particularly weird, shapes that can be represented. So once you flatten them down to cards, you're actually in better shape in some sense, because now you know you don't have any sort of weirdness here. But you still don't really know how you should sort these things, because when you're actually drawing the sprites, they're sort of only approximations to where these things actually were in 3D and what they looked like, right? So at that point, we have to ask, well, okay, let's say that we know that we have, these sprites, and we're sort of talking about them as the Y cards and Z cards, and we have the full bounds of them. And then we look at these two things, and we know that we want to do a sort of these objects, right? Well, like I said before, we can trivially come up with a rule, and this is what we did, that does a correct 3D sort for any two of these things. But in order to actually sort all of the objects in a single total ordering that isn't a graph, but an actual linear total ordering, then we end up with the problem that we don't know how each individual split here will affect the total sort. So let's suppose, for example, that we have, two objects. I'm trying to draw a case here that would make sense. Let's suppose we had two objects that were on the same plane, right? Or better yet, let's draw one slightly higher. Okay? And now we've got an object that's here. And we're looking at it from the camera. Just want to illustrate to you how difficult this problem is, right? So I'm looking at the screen, and I'm saying, between these two, which one should I draw first, right? Well, okay, the first answer is it doesn't matter. Because if the screen looks like this, they don't project onto the same area, right? So it doesn't actually matter which one I draw first. But now you're telling me, well, I need to do a full sort of all the objects in the scene that's topologically correct so that they always draw in the correct order. Well, okay, if that's the case, what I need to do is I need to make a decision about these two such that my decision about these two and my decision about these two will actually yield a correct sort order for these two, which may interfere with each other. And let's make sure that they do, just for fun, right? So I'm going to move this one up a little bit, right? So let's pretend that one was there. And then I'm going to move this one down a bit so they project onto the same area. In fact, you know what? I'll make this one a little longer as well. Okay? So now you can kind of see that these would project onto the same place, right? They overlap. So it's critically important that I know that this one comes first and this one comes second, right? So if this is A and this is B and this is C, then I know that my order has to be that A gets drawn first, right? B or C don't really matter what order they get drawn in now. So it could be ABC or it could be ACB, but but A has to go first, right? That makes sense. So if I look down here and I say, okay, I want to make a comparison between these two guys. Well, I don't have any information to go on, but I could pick some rule about which one I would draw first, potentially, right? Similarly, if I look at some of these other guys, I could make the same thing. They don't actually overlap, right? But I could make a determination about which one of these should go first, like I could. So let's actually look at some of those cases and see what happens. So let's say I take a look at A and C and I go, well, A should certainly be drawn first, and then A second, and then C second, because A is overlapping here, right? That would always give me the correct results, and then when I start B later, I know that I'm okay. But if I start to move A to the side, let's say I move A all the way over so that now it's here. Well, now when I look at how these draw, right, I could certainly create circumstances, depending on where the camera was, right, I could tilt the camera a little bit, where C is definitely the thing that's in front, right? And so depending on whether I want to sort A in front of C or not, depending on its motion here, right, I'm going to end up with a circumstance where I'm either going to see AC at the head or CA at the head, and in different cases, depending on how I draw this, one or the other could be correct. Now I come to B, and I'm like, what am I going to do with B? Well, if I was, looking at B relative to C before I knew about A, right? So I don't know, I haven't looked at A yet. I'm just going to compare B and C together. I might say, well, okay, C clearly comes in front of B, right? I know that that's definitely true. So in this case, right, I know that I would go like CB in this case or something like that, right? Or furthermore, maybe I make the opposite determination, and I could say, B clearly comes in front of C because maybe I'm looking more at it like this. And so I see the B in the front and the C separately, right? So if you do these determinations, where I'm just sort of looking at them in individual pairings, then what happens is, depending on how you picked those pairings, even though it might have been correct for the two as that you looked at, when you then go to insert the third one in, depending on who you were comparing against, right, you may insert it into the wrong place for somebody else. It may be the case that AC is a totally fine order for where you were looking at, right? But B actually needed to be in front of A. So the correct place to put it would have been here, but you never would have known that because you never looked at A and B together. Because that just wasn't what you came up with in the sort order, right? So what you end up doing when you're in a situation like this is you really have no choice, if you're trying to produce a single total ordering, you really have no choice but to actually do basically what amounts to spatial partitions. You would have to essentially build a BSP tree of this scene, I believe, because anytime anything straddles one of these separating plane lines, I'd have to split it into two pieces at least in order to make sure that I always considered it against everything else on the side of this guy. So the only things that I could really know that I don't have to consider are ones that don't break the plane of one of the existing sorts that I've already done. And that's a complete binary space partition of the thing. I don't think there's, I mean, I could be wrong, but I don't think there's any other way to actually do those sorts and guarantee that they'll come out correctly. So because of that, there really is no such thing, I don't think, as a complete 3D sort unless you go into a full spatial partition. So what you're talking about instead is a partial sort where you only sort the guys you care about and prevent yourself from having to do all of these separate splits to sort of deal with people who are sorting otherwise. So that's why you never actually do this in reality, right? This is why you always do a Z-buffer in real 3D. You would never try to sort the 3D objects in a scene. It's like a fool's errand, right? Because you can't actually do it for any sort of complicated objects. And even if you have objects that you know you could sort, you then have to worry about, well, how do I figure out, right, which ones of these go in front of which other ones without actually splitting everyone every time I kind of go down to which ones are on, on which side of which plane, right? So we could try, I don't know if this would actually work. We could try splitting people, or not splitting people, but we could try always sorting by which side of the plane, whichever side of one of these guys you were from the camera. We could try doing a sort like that, which I mentioned before, which is to say, for any given plane, am I in front of the camera or behind the camera relative to that plane? The problem with that, like I was saying before, is that it doesn't really produce correct results in the case where two things overlap, right? If I have two things that look like this, versus two things that look like this, right? It's pretty hard to know without actually looking at the bounds really explicitly which ones are in front of which other ones too, right? So I need to kind of know like exactly where the planes stop and all other sorts of information like this. And again, I don't know. We can try to do more complicated things that will hopefully produce a total ordering, and we'd have to worry again about those splits where we have things that are on either side. I just don't know that we can get any further than where we got, because a very common case for us would be a Z sprite with a Y sprite standing on it, right? That's the standard case of a ground tile and like a monster or something, right? That's what we're going to have. And in that case, you have a situation where these planes split each other into halves, potentially, right? Half of this guy is on this side of the monster, and half of this guy is on the other side of the monster, right? So while we can definitively perhaps write a sort rule that always puts the monster on this side of the plane, what we don't know is what actually happens to which piece here. And like I said, it kind of matters in that sense, because if we then have another sprite and we're comparing it to this, it's critically important, or I guess maybe we'll put it up here, it's critically important that this sprite be compared to this sprite and found to be in front of. But if we were in some scenario where we only were comparing it to this one and we never got there, that would be a problem, right? And so let me give you a scenario where I think that would happen in a very sort of clear case. So here's an upright sprite, and here's another upright sprite, and here's some grounds. So two monsters and two grounds, okay? So it's critically important that this be sorted in front of this, if the camera's here. But, and you know what, let me make it even clearer. Right? But it's also very clear that this is below this. So if this guy got sorted on this side of him, we know that this guy is in front of this guy, right? But this guy is in front of this guy. I mean, that's just how that actually is working for all intents and purposes, right? If he was extended upward, he would be in front of this guy, right? So really what we would need to do in order to know for sure how these sort orders were supposed to go, again, is you kind of have to sort of think about them in terms of how they might get bifurcated, right? So looking at it this way, I'm trying to think of what the best way to illustrate this case is. Once you split somebody by, once you have somebody who extends above where another person's sort was, it's not possible to insert this person into the list in a correct place, because this part of him is above this, but this part of him is below this, right? And that makes a difference not only for how he would draw relative to this, but how he would draw for everyone who's been sorted relative to this guy already. And I feel like there's really just no getting around that problem. I don't know, maybe that makes some sense. Insofar as, sorry if this is already answered, but what was the issue with AZ is not equal to BZ, AZ minus BZ, else AY minus BY style total ordering? So you're talking about basically sort by Z first and then by Y, I think is what you're saying. And the problem of that with that is that you have, so let's say I've got two tiles here. Let me see if I can do it. Sometimes it's kind of hard to draw these things. So here is a Z tile, right? And then I've got somebody standing in front of it or whatever, right? And you know what? I guess probably a better example for that would be see if I can construct this case again. Kind of need a 3D program. Should probably have one. All right. So I believe that this was the problem that we were having with that situation, right? So first of all, we kind of have this problem where let's suppose that these guys are I've done this so many times now I forget like what all the cases are. We probably should have a little thing that we like keep open, which is like here's all the different problems that we have come across or thought about. So we need a couple different things to happen. First of all, we have the notion that there's going to be Y sprites stacked on top of each other, right? So we have the notion that things, and I mean, I guess to draw it all in one scene here, there's going to be something like this that's going to include something like this, right? And the problem with that is, what are the Z values of these two guys, right? Because if the answer is I sort by Z first and then by Y, then if this guy's taller than this guy, he'll always appear in front. But that's not correct, right? Because this guy, although shorter, is supposed to draw in front of this guy if the camera's coming from over here. So you can't just sort by Z value, okay? That's certainly not okay. So then you ask, well, maybe I could sort by the base point Z value. Well, all right, but if I sort by the base point Z value, then we kind of have the question of, well, all right, what does it mean to have a base point Z value? And what happens if that base point Z value is just slightly below where it should be for something else? So for example, let's say I have a step that looks like this. So this is like kind of coming down here. And then I've got my guy here. Well, now his top Z value, right, is above this top Z value, so he should draw first, and that's correct. But now let's suppose I had the exact opposite case where he's on the other side. Now his top Z value is the same as it was before, and he'll draw in front of this, but he clearly should be drawn behind it, right? So you can't just compare one or the other, because whichever one you pick is going to be wrong sometimes. In this case, the Y ordering would have told us, but in the other case, the Y ordering would have been wrong. So you have to have a rule that takes both into account. You can't just go, let's sort by one and then the other. Does that make sense? Insofar as, would the Y then Z sort work if Z is quantized to room layers and sprites are split where they cross layers, and maybe the ground is special cased? No, I think even just a single set of tiles doesn't work. So I don't know. And yes, like I said, I'm going to think about it over the weekend. My answer might be we just want to use the Z buffer. Because since we know the Z buffer is fast, it may be that topological sorting is just going to take too much time. And I don't just mean stream coding time, but I mean like actual CPU time that we don't want to spend. And so we could decide to draw them as cards where we actually place the cards in 3D, and then we let the Z buffer actually do the per pixel determination of who's in front of who. Again, not a great solution for certain cases because of a number of other issues, but it might be the right thing to do. So, all right, I'm going to wind it down. Okay, thank you everyone for joining me for another episode of Handmade here. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with a source code, which you can play around with at home. We also have a forum site you can go to ask questions, a Patreon page you can use to support the video series. We have a wonderful little schedule bot who tweets the schedule at you. And we have an episode guide if you want to catch up on old episodes. That's about it for today. I suspect we'll be back next week, but check the schedule bot for more information on that. For when the next stream will be scheduled. Until then, have a good coding weekend, and I'll see you guys on the internet. Take it easy, everyone.